In the previous videos, we have seen how we can train transformer network encoders for self-supervised prediction tasks. This results in a general protein representation that we can use for many different prediction tasks. In this video, we will shortly look at how we can train encoders for specific prediction tasks that we are interested in and that will hopefully result in protein representations that are even more useful for us. Let us do a short recap of the self-supervised training that we have considered so far. We randomly mask approximately 15% of the amino acids in the input sequence and train the model to predict the type of the masked amino acid. This results in meaningful amino acid representations that contain structural and functional information. After training, we can finally get a single protein representation by calculating the element-wise mean of all amino acid representations. The advantage of this method is that we can generate meaningful protein representations even for prediction tasks where we don't have a lot of labeled training data. The disadvantages of this approach are that we did not train the model for a specific task, and therefore we cannot be sure that the resulting protein representations contain all the information that is relevant for our prediction task. A further disadvantage is that simply taking the mean or the element-wise mean of hundreds of amino acid vectors results in information loss. And specific details about the sequence, such as the exact order or local patterns, might not explicitly be captured in the average representation, even if this information is relevant for the prediction task. Assuming that we have a prediction task with a large training data set, how can we overcome these limitations? We can train such a transformer network encoder that we see here for the specific task that we are interested in and force the model to directly store all the task relevant information in a single vector. Let's have a look at how we can achieve this. First, we notice that we added an additional token to the input sequence, which we name CLS. In the end, we want to use the updated representation of this token to make a prediction for the whole protein. In the beginning, this token doesn't store any useful information, only that this is the classification or CLS token. However, by passing this token embedding through the encoder together with all the amino acid representations, this token gets updated by using information about the amino acids in the sequence. We can train the model to use the updated CLS token that comes out of the transformer network encoder to predict a property of the protein using a fully connected neural network with this vector as the input. The variable that we want to predict here is denoted by y. For example, we could train the model to predict the optimal pH value of proteins. In this case, we would train the model to minimize the mean squared error between the predicted optimal pH for a protein and the experimentally obtained optimal pH. When we train this whole model end-to-end, which means we adjust the parameters of the encoder and of the fully connected neural network simultaneously, we force the model to store all the protein information that is relevant for solving the prediction task in the updated CLS token representation. Training the model in this way, we get a task-specific protein representation by extracting all the information from the protein sequence that is relevant for solving this particular task. After we trained this model, we have two different options. Since this model was already trained for our task of interest, we can simply use this model as our final prediction model. However, sometimes you get better performance results if you extract the protein representation from this fine-tuned model and use it as the input for another machine learning model, for example, a gradient boosting decision tree model. To do this, we can extract the updated CLS token representation for all proteins in our dataset, having now task-specific protein representations that were generated by aiming to extract all information from the protein sequence that is relevant for solving a particular task. When training the protein language model for specific tasks, you wouldn't typically train the whole model from scratch, but instead you would use the parameters of the transformer network encoder that was already trained for the mask token prediction. This way, the model has already a set of useful parameters and has already learned to generate meaningful amino acid representations and to learn to extract information from interactions. This makes it much easier to train the model for specific protein property prediction task. The token that we add to this task is called CLS, which stands for classification, because it was first introduced in the natural language processing domain for classifying sequences. So the concept of adding an additional token at the beginning of the sentence that is then used for a downstream prediction task comes from classifying sentences, and hence this token is often called a classification token, although we can of course also use it for regression tasks such as predicting optimal pH values for proteins.